Hello everyone. Now we have my presentation about modeling on the micro and macro scale. Oh, microphone. Micro and macro scale. But we will start with the basics. Some of the basics you just heard yesterday in the talk of Andreas. I do not need to go too much in detail. So you know about we were in the terahertz range, so starting at 100 gigahertz up to 3 terahertz with our device. We are measuring in the time domain, and then we can also do the Fourier transformation and so on to get the spectrum. But in this case, we just stay in the time domain. You also heard about how we measure. So we get all the depth information at one place if you measure at one place. When we then move the scanner or the head in one direction, we can get this so-called B-scan. So we have a slice in our 3D volume. And if we also move the scanner in the right direction, we got a full 3D volume, and we can also slice in the height or in the other axis. So this is just about the wording. So we have A scan, B scan, Z scan, D scan. But for this talk, we only use the A scans. And we'll talk about these now. You also know this slide from yesterday. So we have, especially in transmission mode, I got the mouse to show you. In transmission mode, we got more or less all the time a similar A scan like this one on the left side. And we can also extract several features of this A scan. We can say, okay, how in time on the x-axis, at which time is the signal maximum or the signal minimum, the signal peak to peak, can we measure? Geez, bless you. We can measure the signal max or extract the signal maximum peak, the signal minimum peak, and so on and so on. We also can do an envelope around this curve, a Hilbert envelope, which also has several features like the half envelope width or the height of the peak and also the time of flight at the peak and so on. So we have several features for every A scan we measure, we can extract and use for our algorithms. Also, Andreas said yesterday, we also can calculate the permittivity in transmission or reflection mode as well. But we will go by machine learning methods or classical methods, and starting with the measurements. We have done measurements for over almost 600 specimens, so really a lot. All these specimens were divided into several groups. So we have 7 material modifications regarding the additives, some with, some without additives. We have different geometric forms. We have tapes and sheets. We have twisted pair cables. We have these coaxial cables. Also, we got 7 aging types. We had radiation aged samples. We have only thermal aged samples. We have combined aged samples, and we have these in low and high aging strength. Maybe I can put on off the mask here. Then we have also 6 aging steps. So we are called them withdrawals, where we put out the samples out of the oven. And all these together is about 60 gigabytes of measurement data, almost 70 gigabytes. So you can imagine it's not manageable manually. So you need some help to watch out for all these features and all these correlations we can get. And that's why we use machine learning algorithms, or in this case, just multivariate statistic algorithms. We will talk about this next. But at first, the data preprocessing. So we developed a small tool where we can load the measurement data. And we see here a peak-to-peak image. So you see the X and Y direction. And in the Z direction, we only use the peak-to-peak value for all depth values. And there we have a picture, and we can choose, okay, where is our sample area and where's our reference area, which is the air around in transmission mode. We also got a picture of the sample in which state it was measured, and the average A scan below, but it's just for the user to see, okay, am I right or not? And then we save all these data in a JSON file. So we have the information, all the meta information, like where's the sample area and where's the reference area, which you can see on the right side. It's an example for such a JSON file. Then we follow the feature extraction, and you know this slide. So we have several features we can extract. And if we do that, in this case, we also save them in a JSON file. There's just an example. You only see the average for every of these features. In fact, we not only save the average, we also save the standard deviation of this feature over the whole sample. And we use this to also calculate the permittivities and try to find any correlations of the permittivity we calculate to all the targets we had, like elongation at break and so on, or to see any trends in the graphs. But I just took this one example, and you see the error bars are very big. Sometimes there is not a clear trend visible, so it's not that good to use as a main feature to correlate with such other targets. And we also saw, I go back 2 slides, we also saw a lot of these features, it's not that much, it's about 8 or something, are dependable to each other. So they are not independent. So that's also not good if you want to make, if you want to have specific features. And that's why we thought, yeah, okay, we got 8 features, but we also extract 8 features out of 1,200 samples per XY direction. So maybe we should use 1,200 features and use all the algorithms for them. And that's what we did in the end. So we had a lot of tables. This is just a screenshot as an example, where we have all the metadata inside, and for every XY direction we have a scan with 1,200 samples, and all of these samples we declare as a feature, as feature space overall. And with all these data, I guess we reduced it to about 2 gigabytes in the end, which is really the raw data and only the important data we can analyze. We thought about feature selection, which is the next step in this whole chain. And the feature selection we use in this case is the principal component analysis. So you can imagine it tries to maximize the component access between the features. So if you look at the right side, you see a graph. It's just an example. You have several features and you have their values, and it's hard to distinguish between them. But if you rotate the coordinate system, it's getting better. So you just if you look at the projection, yeah, if we correlate, we can see, okay, there's one dimension in this direction, so in this rising XY direction, and one on the other side perpendicular to this. And that's what the principal component analysis does with all the features we have. And if you have these components, you can choose how many components you want. You can also plot them in a so-called scree plot. It's like an elbow plot, where you can see how many components do we need to explain the most of the variation between the features. And in this case, we to explain 99% of the variation between the features, we only need 20 components of this 1,200 at the beginning. So in the end, we have 20 polynomials with 1,200 degree, but it's much smaller than these gigabytes of data. So that's what the PCA brings us. So it reduces the whole space to 20 from 1,201. But PCA is an unsupervised algorithm, so it cannot separate all kinds of influence we had by the measurements. But we can use it as a reduction technique, as it's meant to be. And in the end, we also want to classify to classify and correlate the data with other data coming from microscale or macroscale measurements. And therefore, we used just linear discriminant analysis. And the LDA tries to maximize the distance between two classes and to minimize the distance within the class or inside the class. And I guess this is also just an example where you see the projection in this axis is very bad, but if you rotate it, you have a good protection and a good separation between these two classes. For the data we used, I also put in two examples, two plots with on the right side or in the middle. We tried to separate all the data regarding the dose rate the materials have experienced over their aging time. And you can also see we have a very good separation between all these clusters for the different dose rate amount. Or we can use the elongation at break measurement, which we come later more in detail to. We have also made just arbitrary 3 classes. We just said, okay, do make 3 classes, 3 size classes, and say, okay, this is not okay, and this is maybe to monitor in the future. And we also see 3 clusters in the end where you can separate them from each other. But these are just arbitrary limits we choose. For the next slides, this is also just an example. We will use this confusion matrix. So to test your model, you don't use all your data to train the model, because this is like learning by heart for the model. So it's called overfitting. And to pretend overfitting, we reserve 20% of the data as test data and 80% for training the model. And in the end, when you train your model, you just give the model all your test data, and you know the true label, and you look, oh, what does the model predict for this data, for this unknown data, and is it true or not? That's why the confusion matrix is. So you also can see the false positives and the false negatives. And the best way is when the diagonal axis is almost 1. Yeah, then you have an accuracy of 1 or 100% correct. But it's only an accuracy for one. You show it one measurement, and you have to consider that we use per sample at least 1,200 samples or something like that. So it's in the end you make an average of everything. Yeah? Okay, so we just put all the data inside the model and said, okay, all tapes, all sheets, can you distinguish between the form? So do we have a tape or do we have a sheet? And the model can predict that with an overall accuracy of 99.6%. So that's quite good. So, okay, we are sensitive to this. It's more or less obvious. But also the question, if you put all the data inside, so all these gigabytes of data, can you determine how which material it is or which material modification it is? You remember we got 7 different material modifications. But the problem is these are very similar to each other. So it's hard to distinguish, and you see also the model is not able to distinguish them correct. So under 50% is not good. So it's not useful in this case, but we put in all the data, and maybe it's not the smartest way to put in several experiments together in one model.
Sure, I'm not sure.
Yeah, it depends. Sometimes yes. That's why the first step is to put everything inside here. That's the first step. Also, we trained about the aging of the model. So the aging type, we got the, I'll show it with the mouse. We got the aging type 0, which is unaged, and we grouped them together, all the thermal aged ones, the combined aged, and the radiation aged ones. And you see, we can very good distinguish between the unaged and the aged ones, but especially the aged ones are very similar to each other. So there is not that much difference. The same, same for the withdrawal. So we put all the data inside, so also all aging types, and try to distinguish the withdrawal. But in this case, also we can definitely separate the unaged ones from the aged ones, but the aged ones are very similar. So there's a very bluish area in all these withdrawals. So it's not good to predict this out of everything. Then we just looked at material modification 7 in this case. So one material modification, we choose the 7 because 7 has all the additives inside. It has these 2 antioxidants. It also has the ATH inside and so on. And we asked the model how it can predict the aging method. And this is much better. So we have, in this case, a score of 93%. So we see, okay, when we only look at one material modification, it's getting better and better. Also, you can ask the model about the withdrawal, and you also see in comparison to the confusion matrix before, which is all over the place, bluish. We have a very specific diagonal. This diagonal axis nearly coming to 1 or to 90%. So overall, it's about 87%. So we can distinguish between the withdrawals. That's one next step. But what about the micro and the macroscale stuff? We also did it with the elongation at break information we got from VDT. And we just correlated with that. And you can see It's quite confusing because the order is changed. The good ones are the ones below elongation at break of 45, and the bad ones are the one. No, sorry. Other way around, opposite. So the bad ones are below 45, and the good ones are above 45. Sorry, and we can have we have in the end accuracy of the model of 93.8%, which is quite okay. But in this case, or at this time, we didn't had all elongation at break measurements results at this moment. So maybe it's getting better if you have all the left ones. And also we got by Ansem the oxidative induction time. And we also try to use that as a target for the model. And we can distinguish quite properly with 92% correctness. So there are false positives inside, but I guess the amount of oxidative induction time data was not that much overall. So it's like every machine model or a machine learning algorithm, the more data you have, the better your model will be. You know? And with not that much data, it's getting worse and worse. So, but it's able, that's the result, to predict the elongation at break or the macroscale target coming from the destructive testing, also microscale targets like coming from Ansem. So in conclusion, the terahertz measurements produce a lot of data, really a lot, and this amount of data is hard to model with classical methods. You cannot watch in every measurement by hand. There's machine learning and multivariate statistics methods were used in this case. There is the possibility to differentiate various influences in terahertz data recording. The macroscale data, like material modifications, more like metadata and forms and aging methods or dose rates or temperatures, all the metadata we had. And also for the microscale, like elongation at break and oxidative induction time and so on and so on. Yeah, and that's it. I hope I was quite fast. Thanks.
Thank you, Christopher, for your presentation and timing. So the audience is open.
Yeah.
I have some questions concerning algorithm. I'm not sure to understand, did you use a supervised or unsupervised model?
Both. So we used the principal component analysis as unsupervised method to do the feature reduction, to reduce the feature space. And then we used the LDA, so it's like a pipeline after the PCA. And the LDA is supervised.
Okay, and it's a classification or regression?
It's a classification.
Okay,
it's a classification.
Okay.
Yeah.
Okay. Concerning the confusion matrix, in case you present all materials in the same matrix, and you show a score.
This one.
Yeah.
So it's
6%, but it's normal. I think you have some C1, C2, C3. It's different materials. And the aging degradation is different for
every
formulation.
So you mix up everything, so there is no.
So of course your course is bad. No, I'm not saying bad. You have a lot of different formulations, so of course it's bad. But when you focus on one material, the score is very good. So the good scale of study is materials per materials. The first one. And I think if you want to follow, maybe it's okay if we want to study the impact of formulation. Okay, influence the studies influence of matrix, of fillers, and so on.
And you can also imagine about, okay, we have an unknown material, and maybe we try, we use several models for different things, and we try to haggle between all these models to get from the big picture to the small picture. So that's also a possibility, and that's why we started with the whole thing.
May I add something to that? You're saying exactly the right thing. What we can do here is some kind of hierarchical process, right? First, we determine, of course, is it a cable, is it a tape, is it a sheet? Then we can determine after that, is it what kind of material is it? Then after that, when we know, okay, it's material modification X, Y, Z, whatever, then this reduces our possible classes and therefore increases our correct predictions, right?
No.
So you have exactly the remedy.
Yeah.
And did you study the cable system or only plate and sheets?
In this case, only tapes and sheets. The cables is just in progress. So just yesterday and today, and the measurements were done in the last months, and it will be published in the next deliverable 5.6. So we are just in the process of analyzing them. But if you want to see some results, maybe I can show you. Sorry, I can show you some because I just did it. Yeah, the first results are surprisingly good or better than the tapes and sheets. But we need to go more in detail. It was just a first overview. But we use the same concept. So we also use the PCA to reduce it and the LDA to classify. And at least regarding the metadata, like withdrawal or which cable, and are we in the middle of the cable or are we at the beginning of the cable, it looks very good. So all about 90%. But the correct numbers I have to watch in the data.
I have a question.
Yeah.
What do you think about the acceptance process? So it's a model with uncertainties, sometimes good, sometimes maybe much good. And imagine you were an operator and intend to use such models. What could be a good argument for this? Maybe what you are doing here is, as I understand correctly, is you have automatically pattern detection, KE maybe. So what could be a good argumentation that the results are trustable?
Yeah, at least more data. When you have more data, it's better. That's the first answer always.
They want already more data.
Yeah, and then you can also think about if you want to make it more sure, more trustworthy. You can think about doing more analysis on other influences you may not covered before. So if you cover more influences, so also external influences, your model is getting better and better. And as I said before, if we have in this case 93%, so we have of 100 measurements, 7 are false, but we don't have only 100 measurements. We just have thousands. So at one sample. So that's why, okay, maybe you can trust the 93% and not the 7%. It's very unlikely that the 7% are the correct ones.
Maybe to reiterate in that process, with this model, we can only detect what we train for. So if we were now looking at EPR cable, for example, then we would have no idea. Our model would say, error, what is this? So whatever you want to detect, you have to train in the model. This shouldn't pose a problem because, right, you know what you want to detect. In this case, you want to detect cables with an EAB of lower than 50%, for example. And you know, okay, we only have XLPE cables. But as I said, the model, or as Christopher said, the model can be added upon. So if you in the future you see, okay, we need some other samples. We maybe want to detect VR cables too. Then you can rebuild the model and add this new measurement test data and training data.
Yeah, and also add more influences.
Yeah.
Just another project. We were not sure about how good is the operator in putting the sample inside the machine. So we just measured them several times, and they all the time have to put it out, move it around like a baby, and then put it back. So we had this influence of another, maybe slightly other position also in the model in the end. And then it was stable.
In that case, you don't try any prediction. Maybe we can imagine on few samples you don't have in your database, you try to learn, learn with your model. And on few samples, you try to predict the evolution of properties in function, I don't know, of the OIT value or EFP value or something like that. And you try to see if your model can predict the value experimentally obtained.
And how good it predicts,
But you don't try that in that application?
At least a bit, because the test data the model never saw before. So it was not used to train the model. So it was unknown, and it was about 20% of this. And in about the amount of data we got, maybe you can see it here, about, oh God, it's hard to see, 659,153 measurements. So about 700,000, so it's really, really a lot. And 20% of this was randomly chosen as the test data. So the model never saw this data until the confusion matrix kicked in. Only used for testing the model. Okay.
So thank you again.